What do you think heat is? Is heat energy? Or is it a liquid? Watch as we build up a new theory.
Every now and then, an old theory disappears and is replaced by a new one. Few things are as surprising to the outsider as the brazen self-satisfaction of the scientist when such a revolution occurs. He actually manages to look happy. Sometimes he even looks proud. Shouldn't he be ashamed to have been taken in for so long? Well, let's just look back 150 years with Professor Brown to see what happened when science looked for a better explanation of how heat works.
I want to suggest to you how a new theory in science replaces an old one. Theories generally have their supporters, as you can well imagine. And at the end of the 18th century, there were two groups of scientists waging a war of experiment and theory over the question, what is heat? The theory widely accepted at that time was the caloric concept of heat. Its supporters believed that heat was a fluid material which they gave the name caloric. In other words, the caloricists said that the effects produced when you heated an object were produced by adding this caloric fluid to it. Here's such an effect. Heat a piece of wood. It chars. Dip the wood in acid. It chars too. According to the caloric theory, the effect, this charring, is produced by adding this caloric fluid to the wood. Here's another effect. You can see that this bar is attached to a lever in such a way that the lever will show any change in length of the bar. Now, let's heat this bar. Watch the lever. Heat evidently makes the bar expand. The caloricists said that this was because you added caloric to the matter of the bar, and the caloric pushed out the particles of the matter in the metal. In other words, the caloricists said that this caloric fluid was responsible for these effects. Here is a model of matter. The fluid penetrated through all the space and flowed through all substances. When you heated an object, caloric flowed into it. Indeed, it was attracted to it. Caloric had an affinity for matter. At this time, too, scientists believed that the particles of matter in any given object were held together by gravity, and that caloric exercised an opposing force, preventing gravity from forcing the matter into a solid mass. As you've seen, they said that when you heated an object, you added this fluid caloric to it, spacing out the particles of the object as you did so. The addition of caloric made the object expand, just as increasing air pressure makes this expand. Similarly, when you cooled an object, you took the caloric out of it. And when the caloric was drained away, gravity forced its particles more closely together, and it was contracted, just as this does when I decrease the air pressure inside. This then was the theory. Heat was a fluid like a gas. It penetrated all space, it flowed through all substances, and was attracted by matter. There were many other ramifications of this theory. I'll refer to some of them later. But the fundamental point I'd like to make is this. At this time, 150 years ago, there was a pretty widespread belief in the material nature of heat, this caloric theory. I'll give you only an outline of the theory, really a very crude explanation of a very well-reasoned concept. You see, the caloric theory explained very well the effects of heat known 150 years ago. However, the reason I'm here is not to explain the physics of the caloric or any other theory of heat, but to show the dynamic nature of the laws of physics, to show that existing theories are examined, attacked, and ultimately replaced, and to suggest that the replacement of one theory by another is characteristic of physics and science as a whole. In the case of the replacement of the caloric theory with the modern concept of heat as energy, the replacement began as a destructive attack on the materialistic nature of heat. This destructive attack constituted much of the life work of Benjamin Thompson, Count Rumford, born in America, honored in the courts of Europe, a statesman, philanthropist, and a scientist. Rumford did not originate our modern theory of heat, nor did he originate all of the experiments he used to attack the caloricists. The work of Boyle, Hooke, Leibniz, and Locke seems to have had an influence on his work. Nevertheless, his outstanding experimental skill, his endless search for ways to attack the theory held by the caloricists, made him one of the first successful advocates of our modern concept of heat. Rumford's work extended over many years and brought with it not only a basis for a new theory, but also many practical benefits. Right now, however, I'd like you to take a look at three of Rumford's more dramatic attacks on the caloric theory. These attacks struck at the caloricists' concept that heat was a material fluid. If heat were a material fluid, as the caloricists contended, then, Rumford reasoned, it should have properties associated with matter. For example, it should have weight. Even though caloric was not tangible, if it had the property of other fluids, such as water or air, it should have weight. Then, too, Rumford speculated that if heat were a fluid, cooling the body should cause the body to contract and become more dense as the gravity forced its particles together. Rumford suspected that there was an exception to this. For example, water near the freezing point seemed to disprove the law. Furthermore, if heat were a material fluid pervading all matter, there should be a limit to the amount of caloric which could be forced out of any given piece of matter. In other words, if, as the caloricists held, matter were composed of particles bound together by gravity, and yet separated by a certain proportion, if you will, of caloric. Only a certain amount of caloric could be forced out of that matter. Well, first, did heat have weight? Rumford experimented.
Having provided 3 bottles, A, B, and C, as nearly alike as possible, into the first, A, I put a certain amount of water. Into the second bottle, B, I put a like weight of spirit of wine. And into bottle C, I put an equal weight of mercury. These bottles, being all hermetically sealed, were placed in a large room, where the air appeared to be perfectly quiet, and being suffered to remain in this situation more than 24 hours, the heat of the room, 61 degrees, being kept all the time with as little variation as possible. They were all weighed and were brought into the most exact equilibrium with each other. This being done, the bottles were all removed into a room in which the air was at 30 degrees, where they were suffered to remain perfectly at rest and undisturbed.
Well, at the end of 2 days, at 30 degrees, the 3 bottles were still balanced. Naturally, the water had frozen in bottle A. Now, Rumford reasoned that in turning from a liquid to a solid, the water must have lost a considerable amount of heat. If heat were a material substance, a fluid, as the caloricists contended, this loss should have been registered in Rumford's experiments as some loss of weight in bottle A over a 2-day period. The other bottles would also show some loss of weight corresponding to their original caloric content. As Rumford reported, all attempts to discover any effect of heat from the apparent weight of bodies will be fruitless. Another attack on the caloric theory was based on Rumford's studies of water near the freezing point. According to the caloric theory, when a substance was cooled and the caloric fluid extracted from it, it contracted and became denser, heavier. In other words, in the case of water, you would expect that the more you cooled it, the heavier it would get. At least that's what you would expect if you accepted the implications of the caloric theory. Rumford thought otherwise. He reasoned, in the first place, that as water became denser, it would fall through less dense water. And with that assumption, he built the device you see here. A vessel filled with water. A cup-like device standing inside. The whole chilled by ice held in this outer vessel surrounding it. The water in here reaches a temperature of 32 degrees. There's a thermometer to check on this. Now a tin ball with a conically pointed end is inserted into the water. The temperature of this tin ball is 41 degrees. Now when Rumford introduced this tin ball to the water, he knew that it would heat the water, and he knew that as the water rose from 32 degrees to 41 degrees, that he could measure this rise with the thermometer. Now, the caloricists held that the more you cooled a substance, the denser it got. According to them, when this water at the surface of the vessel was heated, it should stay at the surface because it was less dense, less heavy than the water below it. Rumford discovered otherwise. He watched his thermometer.
The conical metal points had not been in contact with the ice-cold water more than 20 seconds when the mercury in the thermometer began to rise.
In other words, the warmer water fell from the surface to the thermometer. The warmer water was actually heavier than the ice-cold water. As you can see, this was completely different from the results the caloricists predicted. They stated, as you know, that the colder a substance was, the denser, the heavier it must be. That bodies always contracted on cooling and expanded on heating. Obviously, water at least was different. It was heavier, denser at 41 than it was 9 degrees cooler. This was a serious objection to the material theory of heat. There were other ways of attacking the caloric theory. One of the most famous of Rumford's challenges concerned, as he put it, sources of heat which is excited by friction. First of all, you can easily grasp the idea that heat is generated by friction. Rub your hands together. You can feel that they warm up. Heat does come from friction. Now, the caloric theory of heat visualized the caloric fluid as being squeezed out of a body by friction, by mechanical work. It followed that if this were so, the quantity of heat produced by friction in any short space of time would be found to diminish gradually if the friction were repeated over and over. Rumford found a unique way of disproving this prediction. He was, at the time, working in Munich as Inspector General of the Artillery and aide-de-camp to the Elector of Bavaria. Part of his duties involved the supervision of the boring of cannon in the military arsenal in Munich. There he was struck by the amount of heat generated in boring a cannon. Rumford argued that if caloric could be squeezed out as heat by friction, then it ought to be possible to show this during the process of boring a cannon. He devised some striking apparatus to test this. With this equipment, which involved surrounding the cannon cylinder with a jacket of water, he was able to note that after the machinery had been running for over 2 hours, the water had a temperature of 200 degrees, and that in 2.5 hours of boring, the water in the jacket had reached the boiling point. So heat was given off by friction, a lot of heat, and it did not seem to diminish as the boring went on, as the caloricists implied. Indeed, to further disprove the caloricists' contention, Rumford carefully examined the chips produced by the drill in the boring process. If the caloric theory were a true one, these metal chips, having yielded heat in the process of being torn from the cannon, should show less heat capacity than the same original weight of the metal of the gun before it was drilled. The caloricists contended, in other words, that the chips had had the caloric squeezed out of them, and that it would not be the same amount of heat as the original metal. Rumford showed that no heat had been lost from the chips in the boring process. This seemed to conclusively prove against the materiality of heat. But the cannon boring experiment was pretty difficult to reproduce. Rumford therefore designed a much simpler type of apparatus to demonstrate that heat produced indefinitely from friction. Here it is. This is a model made for the American Academy of Arts and Sciences to show the experiments which Rumford designed. It consists of 2 hemispheres, one rotating relative to the other. The friction between them produces heat, which will warm up the water, and the amount of warming up of the water can be measured by the thermometer. This takes a fairly long time, but after you have cranked this for some time, you may check on the heat by looking at the thermometer and observing that heat is actually produced by the friction between these 2 hemispheres. Rumford did not believe that this experiment had produced any new insight into the nature of heat, but rather was a serious blow to the then current caloric theory. He put it this way.
In reasoning on this subject, we must not forget to consider that the most remarkable circumstance is that the source of the heat generated by friction in these experiments appears evidently to be inexhaustible. It is hardly necessary to add that anything which can continue to furnish without limitation cannot possibly be a material substance.
So, on 3 counts at least, the caloric theory was shaken. Rumford found that he could not weigh heat. Then he found that bodies did not always contract when cooled and expand when heated. And finally, he saw that heat in a substance was apparently inexhaustible. These were telling attacks on the existing theory. However, nowhere in Rumford's writing can you find a step beyond this. Nowhere do you find that he had the concept of a direct relation between mechanical work and heat. But the destructive attacks on the caloric theory made by Rumford were an essential and characteristic step in the process of building up a new theory. What Rumford did was to demonstrate that the older theory had to be replaced. When an established theory comes under attack in this way, a long period of detailed experiments usually follow. These experiments, carried out by many scientists in many countries, usually lay the foundations for new ideas. In the case of the theory of heat, the most outstanding of these were done 50 years after Rumford by James Prescott Joule in England. Joule demonstrated the mechanical equivalence of heat. His work was characterized by notable precision and imagination. After Joule's work, theoretical physicists of the stature of Helmholtz and Clausius fitted all the observations into an exact mathematical structure which described heat as energy. Thus, from the mechanical and concrete experiments of Rumford came the highly theoretical and mathematical concepts which characterize our modern theory of heat. For the past 80 years, this theory has withstood the attempts at destruction which physicists continually direct toward their theories. Today, our theory that heat is a form of energy survives. But of course, it is possible that this theory, like others in physical sciences, will in turn meet its match in the challenges of some new Rumford.
So this is the story of how Rumford scotched, if not quite killed, the caloric theory. You can see now why physicists have no reason to be ashamed of an old theory. The old theory, caloric in this case, had explained quite well a number of familiar facts of observation. Actually, it still does. What Rumford did was to produce some new experiments, which on 3 main points clashed with the caloric theory. But Rumford had no better theory to put in its place, and this had to wait for the work of Joule and his followers, as Professor Braun just told you. This new theory, which replaced the caloric theory, was the principle of the conservation of energy. It became generally accepted around 1850. By that time, chemists had become convinced of the truth of another principle, that of conservation of mass, announced by the French chemist Lavoisier in the 1780s. By the last quarter of the 19th century, scientists had become completely certain that the laws of Newton in mechanics, together with the conservation of mass and the conservation of energy, were 3 truths more solid than bedrock. And they were so certain because these 3 laws had been found to explain innumerable effects covering a boundless variety of circumstances. Nevertheless, around 1900 it became apparent that there were, after all, exceptions to these laws. Those exceptions developed into an entirely new chapter of physics. This was concerned with attempts to make electricity pass through a very high vacuum, and it pointed to the existence of a new particle, the now very familiar electron. These electrons behaved in what were then considered as very strange ways. It was Einstein, the Newton of our age, who developed a new theory which explained at one stroke these new phenomena as well as all the old findings of classical physics. The laws of Newton, the conservation of mass and of energy, were not really universal as we had thought. They were not absolutely true. The correctness of Einstein's views has been checked many times during the last 50 years. But we are not by any means so certain today of the general validity of Einstein's theories as our grandfathers were of those of Newton's laws and the conservation of mass and of energy. These ups and downs on the acceptance of physical principles explain the attitude of the scientists to ancient theories. He has no reason to be ashamed of them. They are still today as capable as they ever were to account for those phenomena which were known at the time they were in vogue. Only, we learn more every year about domains of nature which formerly we had not even suspected. Thus, we have to devise new ways to account for nature's ever-surprising variety. We look at such newly discovered phenomena in much the same way as Rumford's contemporaries did. They understood problems about mixing hot and cold water, but were amazed at the heat produced in boring cannon. We owe all, or almost all, the advances of science to the few men who have, as Rumford had, the ingenuity to devise experiment in uncharted scientific territory and the temerity to dissent from hallowed scientific theory.
This is National Educational Television.